Hello, everyone, and thank you for joining me for this presentation on in vitro hemolysis and clinical chemistry testing. My name is Stacy Kenyon, and I am the Section Director for Clinical Chemistry and Point of Care Testing at Phoenix Children's. One of my laboratory medicine interests involves specimen integrity, which is why I will be talking to you today about specimen hemolysis. Today's presentation is primarily intended to be an introductory talk on hemolysis in the clinical laboratory. During the presentation, attendees will be able to describe common pre-analytical causes of hemolysis. They will also be able to describe how and why hemolysis interferes with the measurement of some different clinical chemistry analytes. And finally, we will review strategies to reduce hemolysis in repeatedly hemolyzed specimens. In particular, we'll focus on processes that have been used to reduce in vitro hemolysis in specimens from hospitalized patients that have a history of repeat hemolysis, and this process is called special handling instructions. Before jumping into hemolysis, I want to take a moment to briefly talk about the total testing process, which includes all the steps involved in the clinical laboratory testing process. That includes from specimen ordering all the way to specimen resulting. It is generally broken into three phases: pre analytical, analytical, and post analytical. Pre analytical involves all steps that occur before the specimen arrives in the laboratory. Analytical includes all the steps involved in the testing of the actual specimen, while post analytical includes all steps that occur after the specimens are analyzed. Although the laboratory has the most visibility and control over the analytical phase, many laboratory errors actually occur in the pre-analytical phase before the specimen even arrives in the laboratory. Some common pre-analytical errors include hemolysis, clotting, and contamination. The pre-analytical phase is particularly prone to errors due to the numerous manual steps involved in this process, including sample collection, handling, and preparation, as well as sample transportation and storage of the specimen before testing. Ultimately, the lab is concerned with pre-analytical errors because they can lead to specimen rejection and erroneous results. Specimen rejection is a patient and physician dissatisfier for many reasons, including redraws, delayed results, and ultimately delayed medical decision making. I'll be mostly focusing on redraws today. We all know that redraws can be particularly problematic for some patient populations, such as those that don't have easy venous access or those that are at risk of iatrogenic anemia, such as in the neonate population. So it's very important that we are able to reduce specimen redraws. As part of quality programs, laboratories monitor rejection and redraw rates and reasons for the rejections. The info that is available in the literature overall suggests a very low rejection and redraw rate. Of course, these rates are going to vary by patient population, type of testing, and patient status. For example, inpatients are generally going to be at a higher risk of specimen rejection and redraw than outpatients. This is often just because of the clinical situation of the patients, as well as the more complex specimen collections that have to occur. Oftentimes, inpatients have to be collected by line draws, and this can lead to additional specimen rejection issues. Based on my previous experience, hemolysis tends to be the most common reason for redraws in most patient populations, particularly inpatient populations. Hemolysis is the process by which membranes of red blood cells are ruptured, thereby releasing their contents into the surrounding fluid. When the red blood cells rupture, hemoglobin is released into the surrounding plasma, as well as other components that are contained in the red blood cell, such as analytes, including potassium and lactate dehydrogenase. As mentioned previously, hemolysis is a relatively common pre-analytical error that leads to specimen rejection in the clinical laboratory. In fact, hemolysis is the most common cause of redraw for all inpatient populations in the data set that I'm sharing on this slide. This is 1 year of data, and in this 1 year, there were over 730,000 inpatient collections performed. Of those 730,000 draws, 9,800 were redraws, meaning that a specimen was sent to the lab, was unsuitable for testing, was rejected, and a redraw was requested and performed. This data tells us that the overall redraw rate is quite low. It's just 1.3% of the total draws. Of the 9,800 redraws, 4,500 of them were redrawn due to hemolysis. This accounts for just 0.6% of all draws, but nearly half of all redraws. So even though our overall redraw rate was low, hemolysis was often the cause for the redraws. To better understand why hemolysis leads to such a high percentage of rejected and redrawn specimens, it's necessary to understand how and why hemolysis occurs. Hemolysis can be the result of in vivo or in vitro processes. In vivo processes are primarily going to include pathological conditions such as hemolytic anemia, hemolytic disease of the newborn, and enzyme deficiencies. In vivo hemolysis can also be the result of mechanical stress, such as occurs post-surgical procedures and in patients that are on ECMO or bypass. In vivo hemolysis generally occurs infrequently and accounts for a small percentage of redraws and the hemolysis that we see in our specimens. It's important to note that in vivo hemolysis occurs in the patient, while in vitro hemolysis, on the other hand, occurs when the specimens are are either being drawn or after they've already been drawn. So they do not represent the physiological condition of the patient. In vitro hemolysis is also much more common than in vivo hemolysis and is estimated to account for more than 90% of specimens that are rejected due to hemolysis. Reasons for in vitro hemolysis include collection procedures, such as line draws, difficult sticks, or the use of butterflies for collection. This can all lead to rupturing of delicate red blood cell membranes. Studies also show that transporting samples via pneumatic tubes, particularly from patients that have fragile cells or lipemic specimens, can also lead to additional in vitro hemolysis. We have established that hemolysis is problematic because it can lead to specimen rejection, specimen recollection, and delayed resulting. This is ultimately because the results can be inaccurate when the specimens are hemolyzed. On this slide, there are just 4 chemistry analytes that are listed, along with the impact of hemolysis on these analytes. Hemolysis can lead to falsely elevated potassium, AST, and LDH due to the relatively higher physiological concentration of these analytes and RBCs versus the surrounding plasma. This means that in these 3 cases, hemolysis is actually a physiological interference for these analytes. While direct bilirubin is falsely decreased in the presence of hemolysis, and in this case, it's just an analytical interference because um, this analyte is not contained within the red blood cell, while potassium, AST, and LDH are. It's also important to know that the acceptable extent of hemolysis is analyte dependent. This table shows examples of acceptable hemolysis thresholds for 5 different analytes. You can see that the extent of acceptable hemolysis varies significantly, from 15 for AST to 1,000 for alkaline phosphatase and total bilirubin. The extent of acceptable hemolysis is impacted by multiple variables, including whether hemolysis is a physiological or an analytical interference, as we discussed on the previous slide, as well as if it's a physiological interference, what the concentration of that analyte is within the red blood cell. So how do we determine the extent of hemolysis? It can be estimated by visual inspection. Due to the hemoglobin found in the red blood cells, when the extent of hemolysis is increased, or there are more red blood cells that have ruptured in the specimen will appear more red. In the image shown here, the specimen on the left is non-hemolyzed plasma, while the specimen on the right contains hemolyzed plasma, so you can see it's more red. Historically, the extent of hemolysis has been estimated by a visual check. So the plasma specimen would be compared to a chart, and then the extent of hemolysis would be estimated based on a chart. More commonly today, the extent of hemolysis is measured spectrophotometrically on analyzers and reported out either semi-quantitatively or quantitatively. The reported value is referred to as the hemolysis index or the H index. It is approximately proportional to the amount of hemoglobin in the plasma specimen. To better understand the impact of in vitro hemolysis on an analyte, I want to go through potassium as a case study. I chose potassium due to its importance in regulating many bodily functions, such as heart function. Inaccurate potassium results can lead to inappropriate medical interventions or lack of interventions. So it's very important that we are able to report out accurate plasma potassium results. I also chose potassium as a case study because hemolysis is a physiological interference. So there's higher concentrations of the plasma potassium, or excuse me, higher concentrations of the red blood cell potassium than the plasma potassium. In fact, 98% of total body potassium is found within the intracellular fluid, while only 2% is found in the extracellular fluid. So, normal plasma potassium or our extracellular fluid potassium, the normal range is 3.6 to 5.2 millimole per liter, while the concentration of potassium found in the red blood cell is approximately 105 millimole per liter. Due to this 20-fold difference in potassium concentration between the red blood cell and plasma, it suggests that relatively low levels of hemolysis could lead to falsely elevated plasma potassium. To evaluate this interference, so the interference of hemolysis and plasma potassium measurements, we performed a hemolysis spiking study in-house. 3 plasma potassium concentration pools were created, which are listed here. A 2.5 millimole per liter pool, and this was selected because it would be considered a critically low plasma potassium value, and then 2 plasma potassium concentrations that were within the reference interval, a 3.4 millimole per liter pool and a 5.1 millimole per liter pool. For each plasma potassium concentration pool, 7 H indices were prepared, varying from non-hemolyzed to grossly hemolyzed. So for each of these 3 plasma pools, there were 7 varying levels of hemolysis for each pool. This study ultimately demonstrated that as the specimen became more hemolyzed, the potassium concentration increased. We made this assessment by comparing the hemolyzed results to the non-hemolyzed results for each plasma potassium concentration. The plot on the right summarizes the study. In this plot, there are 3 lines representing the 3 potassium concentrations tested. The blue line represents the 2.5 millimole per liter potassium specimen. Again, this would be when it's not hemolyzed. The orange line represents the 3.4 millimole per liter potassium specimen pool, while the gray line represents the 5.1 millimole per liter potassium concentration pool. The x-axis includes the various H indices that were investigated, while the y-axis is the difference in potassium concentration. This is the difference in potassium concentration between the non-hemolyzed specimens and the hemolyzed specimens. We specifically compared the various levels of hemolysis for each plasma potassium concentration versus the non-hemolyzed sample of the same concentration. As you can see, as the H index increased or the extent of hemolysis increased, so did the plasma potassium concentration. Based upon what we know about the red blood cell concentration of plasma or the red blood cell concentration of potassium, this is to be expected. It's easy to see that the hemolysis leads to an increased plasma potassium result, but at what point does the difference between the non-hemolyzed and the hemolyzed plasma potassium results become significant? If we use the CLIA total allowable error of 0.3 millimole per liter potassium, which is highlighted on the plot with the red horizontal line, you can see that the threshold for hemolysis is quite low. In fact, this would correspond to an H index of approximately 53. So what this ultimately means is that all of the results for all 3 plasma potassium concentrations that are above the red line would be considered different, significantly different according to CLIA. Of course, the cutoff that is used can vary by different institutions. CLIA is just one way to make the determination. Some laboratories may use 10%, or they may use the older CLIA guidelines, which were 0.5 millimole per liter. What this ultimately shows us, though, is that due to the high intracellular erythrocyte concentration of potassium, the acceptable acceptable threshold of hemolysis for plasma potassium measurements is quite low. This is why hemolysis commonly leads to rejection and redraws for potassium because it can lead to inaccurate, falsely elevated results. It is therefore very important to make sure that the hemolysis is reduced as much as possible, particularly in vitro hemolysis, as it does not represent the physiological picture of the patient. Because in vitro hemolysis accounts for more than 90% of hemolyzed specimens in the laboratory, and samples with in vitro hemolysis do not represent the clinical picture of the patient, there are many well established practices that help reduce in vitro hemolysis. Most revolve around reducing the mechanical stress that is put on the specimen. And that includes there's a large focus on the specimen collection process as well as the specimen transportation process. This slide lists a few examples, including avoiding line draws during specimen collection, if it's possible, using appropriate gauge needles, and then selecting appropriate draw sites during the collection. Additionally, during the transportation process, limiting the number of transport steps that can jostle and disrupt the red cell membrane and also can help reduce in vitro hemolysis, and then also evaluating the impact of transporting specimens via pneumatic tube, particularly lipemic specimens, as I briefly mentioned before, or specimens from patients that may have delicate red blood cell membranes due to various pathological conditions. However, these strategies for reducing hemolysis are not always successful. So what happens if none of these processes work and the specimens do arrive in the lab hemolyzed? How do labs handle specimen rejections and redraws due to this hemolysis? I've shown an example here on this slide. The process for identifying and redrawing hemolyzed specimens involves the use of analyte-specific hemolysis thresholds, as we discussed previously, as every analyte has a different acceptable threshold for hemolysis. When hemolysis exceeds these thresholds, a middleware rule prevents the release of the results, and an automatic redraw is issued. If the redraw has hemolysis below the acceptable threshold, the result is auto-verified and released. This is what happens to most specimens in the laboratory that are initially hemolyzed. However, what happens if the redrawn specimen is still hemolyzed above the acceptable limit for that specific analyte? The middleware rule will again prevent the release of the result, and if both hemolyzed draws are within 24 hours, another rule is triggered and the lab contacts the clinical chemistry fellow on call. From there, the clinical chemistry fellow assesses the clinical picture of the patient with the clinical service, and there are generally three different things that can happen. One, the clinical service cancels and will just order a draw later in the day. The second scenario is that service would like a redraw, so a redraw is issued, and we specifically request for the redraw to be collected by venipuncture to help reduce some of that in vitro hemolysis, particularly the causes that are associated with line draws. Or the third scenario is if the sample from the patient has been repeatedly hemolyzed and all of the other interventions to help prevent in vitro hemolysis have not been successful, the clinical chemistry fellow may issue a process called Special Handling Instructions, or SHI. Special Handling Instructions were developed after a QI project between lab and NICU to reduce in vitro hemolysis in specimens drawn from NICU patients. During the project, the team investigated three potential contributors to hemolysis: intravenous lipid infusions, rate of sample collection through indwelling catheter, and transportation of specimen to the laboratory. During the investigation, the authors determined that high catheter withdrawal rates contributed to in vitro hemolysis, as well as collecting samples during lipid infusions and then transporting them via pneumatic tube. These findings ultimately led to a more formalized and standardized process for collecting specimens from patients with repeat hemolysis. And this process, of course, is the SHI process, or the Special Handling Instructions process that I referred to earlier. The overview of the process is shown on this slide. The Special Handling Instruction process starts with the clinical chemistry fellow initiating special handling instructions after discussion with the clinical team. The The steps involves filling out a form with the analytes that have been repeatedly hemolyzed, emailing to a distribution list, and then calling IT and lab support to add a comment to the patient in the LIS so that when phlebotomy goes to collect a sample from the patient, they know to collect the sample as a gel-free lithium heparin plasma specimen. Ideally, this would be collected via venipuncture. As discussed, line draws can often lead to additional in vitro hemolysis. Once the specimen is collected, the phlebotomist would then hand carry the specimen to the stat lab instead of sending via pneumatic tube. In the stat lab, the specimen is centrifuged and plasma is aliquoted. Any testing that can be performed in the stat lab is completed, and then if there are any tests that need to be performed in a different laboratory, the plasma aliquot alone is sent to the lab via pneumatic tube for further testing. So the key points here would be that the specimens are collected ideally by venipuncture using a non-gel lithium heparin tube, and then the specimens are hand carried to the lab where they can then be centrifuged and separated from the red cells. As you can see, the special handling instruction process is quite manual, involves the coordination of multiple departments. The process is of course worthwhile if no other strategies for reducing in vitro hemolysis are effective, and if the process leads to fewer rejected and redrawn specimens for the patient. To evaluate the effectiveness of special handling instructions, a small in-house study was performed. The study and the results will be shared on the next few slides. The process for evaluating the effectiveness of special handling instructions involved a prospective study that reviewed all special handling instructions issued during an 8-month period. This resulted in 98 special handling instruction examples being included in the study. Data pre and post special handling instructions was included. For this study, pre-special handling instructions refers to the sample that initiated special handling instructions due to hemolysis and was the last sample collected from the patient prior to issuing special handling instructions. Post-special handling instructions refers to the first sample collected from the patient after issuing the special handling instructions. Data regarding the analyte that initiated special handling instructions, or the analyte that repeatedly had hemolysis above the threshold, and as well as data regarding the extent of hemolysis as measured on the Roche Cobas and reported as H-index were all collected for the study. All of this data was collected from the LIS or from instrument software. From there, calculations were completed, including the change in hemolysis pre and post special handling instructions initiation and the percentage of reportable results after implementation of special handling instructions. Shown here are the analytes that initiated special handling instructions in the 98 cases that were included in the study. As you can see, hemolyzed potassium was the analyte most likely to initiate special handling instructions, which should be of no surprise based on the hemolysis spiking data that was shown earlier in the presentation. After potassium, AST was the second most likely analyte to initiate special handling instructions. I think it's important to note that both of these analytes would be considered, hemolysis would be considered to be a physiological interference, and because they have higher red blood cell concentrations than what you find in the plasma. So after the implementation of special handling instructions, hemolysis was significantly reduced. On this plot, we show that pre-special handling instructions, the H-index varies from approximately 55 to 1,700, with a median H-index of 215. Post-special handling instructions, the range of H-indices is much less at 0 to approximately 350, with a median H-index of just 18. The median percent decrease pre and post special handling instructions was 93%. This decrease was shown to be significantly different. However, does this significant decrease in hemolysis lead to more results being reported and the patient being ultimately redrawn fewer times? To phrase it another way, how many specimens had hemolysis below the acceptable threshold after the implementation of the special handling instructions? It was ultimately determined that the significant reduction in hemolysis led to the auto verification and reporting of most results. Overall, 86% of the results were able to be reported automatically post special handling instructions due to the decrease in hemolysis. So, in conclusion, from this study of 98 cases of special handling instructions, we were able to demonstrate that specimens collected using this process had significantly reduced hemolysis. The reduction in hemolysis allowed for most patient results to be reported, which ultimately prevented additional redraws and faster resulting. With that, we will wrap up this presentation on Introduction to Hemolysis in the Clinical Laboratory. From this presentation, one should learn that hemolysis is a common pre-analytical variable that leads to specimen rejection and recollection in the clinical laboratory. Not all analytes are created equal, as different analytes are impacted differently by hemolysis. There are strategies to help reduce in vitro hemolysis, ultimately reducing rejection and redraw rates. One process in particular, called special handling instructions, is an option for use in patients that have repeatedly hemolyzed specimens. And with that, I would like to thank the many people that have contributed to the two different sets of data and projects that were shown in this presentation. Thank you.